Alrighty, welcome back, boys and girls. It's your main math man, Mr. Shank, coming to you live from Summit Academy. In this video, still working on that unit number 5, talking about our functions and being able to compare them. And we're working on lesson 9 now. So it says a candlelight. So it says a candle is burning, and then it starts out 12 inches long. After 1 hour, it is 10 inches long, and after 3 hours, it is 5.5 inches long. And so what we can do is we can kind of write some points down that we have. So I can say, well, I can have some ideas like this. I can say, well, if I start out at 0, my y value is 12, and as it moves along, it said, okay, I have 1, and it was 10, and it said 3, and let's say about 5.5. So how long do you think it will burn out, or how long do you think it will take to burn out completely? Well, if you notice, we can say, well, it's decreasing by 2, so we're saying this is like -2 and this is +1, so that slope is going to be -2. And again, it's approximate because, you know, notice how it jumps up to 3 and it jumps down to 5.5, and so what we can say is, if we follow that pattern, it will take about 5 or 6 hours. So let me follow this out. So if we go, if this goes to 4, we'll say this is 4, and my next one would be about, what would we say, 3.5, and then we go to 5, and 1.5, yeah, around hour 6 for sure, it will be at least 0. So again, it will be in between 5 and 6 hours. So notice how I was able to kind of make that pattern. Again, as my x values increase, meaning as time goes along, my y values decrease. Then it says, is the height of the candle a function of time? If yes, is it a linear function? And explain your thinking. So we're going to say that a height is a function of time. However, it is not a linear function because the rate of change is not constant. If I look at that, I could say, well, that makes sense because when I look at when I go from 10 to 5.5, again, that jumped. So even though it was 2, it increased by 2 on the x, it should have decreased by 4. So it should have been 6 if it was constant, but it wasn't, so we're going to say it's not linear. Okay, underneath of that it says, we're talking about shadows now. So it says, when the sun was directly overhead, the stick had no shadow. After 20 minutes, the shadow was 10.5 centimeters long, and then after 60 minutes, meaning 1 hour, it was 26 centimeters long. So the picture goes along with this situation, and so it says, based on this information, estimate how long it will take or how long it will be after 95 minutes. So I'm going to approach it the same kind of way. I'm going to kind of write our table here. Again, it starts at 0, 0 because the shadow is 0 centimeters long. However, after 20 minutes, it's 10.5, and after 60, it's going to be 26. So again, if you wanted to, you can say, well, you know, how long would it take? Or how, if I go 95 minutes, well, I could say, if I find my slope, so I'm going to say my slope is going to be the change in y, which is 10.5 over 20, which is going to be the same as multiplying by that fraction. So I can say, if this is our fraction, I can say I can multiply and say if 95 times 10.5 over 20 is going to be about 50 centimeters long. Again, I rounded to the nearest whole centimeter, but that's okay. So now for the next part, it says after 95 minutes, it actually measured to be 38.5. So how does it compare to your estimate? Well, we're going to say we overestimated by 11.5 inches because the difference between those two was 11.5. Then it says, is the length of a shadow a function of time? If so, is it linear? And explain your reasoning. Well, we're going to say it is a function of time. The length is a function of time, meaning our y values was the length, where our x values, our independent variables, was the time. However, it is not a linear function because when we plot the points, they do not form a straight line. So a couple different things you can say. You can talk about the rate of change. You can talk about the points not being a straight line. Multiple ways of approaching this. All right, for the next part, it says recycling. So we're going to say for this part, it says in a earlier lesson, we saw this graph that shows the percentage of all garbage in the U.S. that was recycled between 1991 and 2013. So first, we have to sketch a linear function that models the change in the percentage of garbage that was recycled between 1991 and 1995. So let's graph that out. And it says, for which years is the model good at predicting the percentage of garbage that is produced? For which years is it not good? So let's graph it out first. So let's graph a pink line maybe. Let's just do orange. That's fine. So I can go from, let's say, from 91 to 95. So I'm going to graph that line. Let's try that again. So pick that point 91, and I have to go through that point 95. So let's go through that point, something like that. And I could say, well, graph the line first. So it works from 91 to 95. However, it's not that good of a graph otherwise, because if I look at, from 91 to 95, it's pretty close to that, line that we drew. However, as soon as we get to 96, that's when it kind of becomes a little bit rougher. So we're going to say that this one is for number 1. This one is for number 1. And for number 2, it says pick another time period to model with a sketch of a linear function. For which years is the model good at making predictions, and which is it not good? So let's graph another line first. So let's go from 94, I believe. Let's go about 94, 95. And we go the whole way out like that. So same kind of idea. We graph it first. It's a good approximation from 94 to 2013. However, besides that, it is not that good. So this one's going to be number 2. So again, notice how these points are close to the line. However, these points on our first line are not close to our green line. All right. So now for the practice part, it says on a first day after the new moon, 2% of the moon's surface is illuminated. On the second day, 6% was illuminated. So that means this, we can say that means that it's going to be 4% each day, assuming it's going to be a constant rate of change. Then it says, based on this information, predict the day on which the moon's surface is 50% illuminated and 100% illuminated. Well, if we read this as well, we can say after 11 more days, after day 2, it reaches 50%. So we have to combine those two together. So we're going to say day 13 is equal to 50% illuminated. However, we double that, so we're going to say day 26 is 100% illuminated. Then it says the moon's surface is 100% illuminated on day 14. Does this agree with the prediction made? We're going to say no for that one. We're going to be off by almost 12 days. And then it says, is the percentage illumination of the moon's surface a function of the day? We're going to say no. The linear model did a bad job at approximating the data. So let me type that in there too. Approximating the data. Okay. All right, moving to the back now, it says in a science class, JD uses a graduated cylinder with water in it to measure the volume of some marbles. The first part says after dropping in 4 marbles, so they are all underwater. The water in the cylinder is at a height of 10 meters. And then it says for the next part, after dropping 6 marbles, so they are all underwater, the cylinder is at a height of, or the water in the cylinder is a height of 11. So we're going to say, and what we can do is kind of make that table again, real simple. It says 4, 10, and 6, 11. So be able to find your change in y, it's going to be plus 1, and our change in x is going to be plus 2. So that means our slope for this is going to be equal to 1/2, or 0.5. And so what is it? The volume of one marble? Well, we can say one marble. If we were to plot that point, we could say it's one marble is going to be equal to 0.5 milliliters. And it says for the part B, how much water was in the cylinder before any marbles were dropped in. So we have to kind of go backwards, and a way we can do that is like this. So let me actually clear this out, and let me write it like this. I can say, if I start at 4 marbles, we were at 10, and what I can do is I can count backwards. So I can say, well, if I go -2 in this direction, I have to go -1 in this direction. So now the pattern is going to be like this. I have 2, 9, same idea, 0, 8. So notice how I can go in that reverse direction. If I go down the ladder, I can also go up the ladder. So I'm going to say for this one, it's going to be 8 milliliters. L. And it says for part C, what should be the height of the water after 13 marbles are dropped in? So we're going to say, let's actually go down now. We have, let me change this graph a little bit one more time. So I can start from 6 and 11. Show me a little bit tighter there. It is. Okay. So what I can do is count by 2, so I can say 8 and 12. I can say 10 and 13. And say 11 and, or no, sorry, 12 and 14. And then I can say the next one would be 14, 15. But I need to take it in between those two. So I'm going to say it's going to be after 13 marbles dropped in, I would have 14.5 milliliters. So be able to use that graph. Again, you can take points in between them because it makes that line. And we're going to say, talking about that line, it says, is volume of the water a linear relationship with the number of marbles dropped into the graduated cylinder? If so, what does the slope of the line mean? Explain our reasoning. So we're going to say yes, and then the slope of the line means the volume per marble. And that's how we found that 0.5. For number 3, it says solve each of these equations by graphing and write that solution point as an ordered pair. So let's pull up our wonderful Desmos calculator. I'm going to graph out this system. So again, make sure you graph it out like this. I'm going to say, okay, this is going to be one equation. So this is going to be, let's say first line, and then we can highlight our other side of our equation and say it's going to be our second line. All right, so let's go to our wonderful calculator, type in what we have. So we're going to say we have 2 times the quantity 3x plus 2. And we hit enter to get our new equation. Our new equation is going to be 2x plus 28. Let me change this to green and that one to pink. Okay. And if I need to, again, I can zoom around or zoom out, find your other line, find where they intersect. wherever they meet is going to be our solution point. So we're going to say for this one, our solution point, or our answer, is going to be the point 6, 40. All right, so make sure you can see how to do that. Make sure you can pause for your turn. So let me write that down too. So pause for your turn. Graph and check with me. So make sure you're graphing those points, again, as an ordered pair, X and Y. All right, so now that you graphed those systems, it says for a certain city, the high temperature in degrees Celsius are plotted against the number of days after the new year. Based on this information, the high temperature in this city is a linear function of the number of days after the new year. So let's graph our line first. So let's actually clear some of those real quick. Okay, if I go to graph this line, I can say, hey, I connect my points and graph it like that, and I can say, well, hey, so let me write that. The points are all on the same line. And what that means is this. We can say, since the graph is a straight line, it's going to be a linear function. So let me write that in as well. Should say a linear function. So anytime you see that word linear, just think a straight line. Real easy to remember. All right. And then for number 5, it says the school designed the vegetable garden to have a perimeter of 32 feet with the length measuring 2 feet more than twice the width. If we're using L to represent the length of the garden and W to represent its width, write and solve a system of equation that describes this situation. So what we can do is this. I can write my system like this. I can say, well, if we have, again, system means 2 equations, 2 more equations, but I can have 2 times L plus 2W equals 32. So that's going to be that first equation. Again, I get that from the perimeter 2L plus 2W from length and width. And then we can get the second one. We can say L is going to be equal to 2W plus 2. Now, if I want to graph it, I want to graph this system, I can change it so that way I can use X and Y. So let's actually say, let's let X be the length and let's let Y be the width. So if I want to, I can write my system like this. I can have 2X plus 2Y equals 32. And then I can say X equals 2Y plus 2. So now I can actually graph it on Desmos. So let's take this graph, let me reshare it. Let me reset this one real quick. Hit that home button to get back to your origin. So I have the system of equation of 2x plus 2y equals 32. And then I have x equals 2y plus 2. All right, so find where these 2 points are, or where these 2 lines are equal. At this point, 11.333 and 4.6667, I can say that, hey, at that point is where they're going to be equal. So find where they're equal and say that's going to be solution point. So I'm going to say, let's solve it. What are the dimensions of the garden? So this has a solution point of let's say 11.333 and 4.667. That's going to be the same as saying the length, so let's do a different color here. We're going to say the length is going to be equal to 11 1/3 feet. And then we can say the width is going to be equal to 4 2/3 feet. So make sure you can switch between those decimals and fractions. Be sure to check with me if you have any questions, and as always, make sure you can read the exit ticket first. So it says a small company is selling a brand new board game, and they need to know how many to produce in the future. After 12 months, they sold 4,000 games. After 18 months, they sold 7,000 games, and after 36, they sold 15,000 games. Could this information be reasonably estimated using a single linear model? And if so, use the model to estimate the number of games sold after 48 months. So there's the translation for you. Be sure to ask questions if you need to, and as always, super slam that subscribe button.